Hello, everybody, and welcome. This is Professor Thayer, and today we are going to do Dominic quantum mechanics. So we are in the middle of a snowstorm right now, just starting to break and cleaning up. So I'll just trudge to work. You can see my coat in the background, and I also have my snow pants with me. So this is what's happening in my world. So let's dive into the dawn of quantum mechanics. I'm going to go ahead and share my screen. And let's get the slides up. Sorry, I got two screens going here, and that is backwards for you. So let's fix this. All right, and I'm going to turn the timer on so I don't talk too long. All right, so quantum mechanics. When did it start, and who cares? So this is a very famous quote from Albert A. Michelson. The more important fundamental laws and facts of physical science have all been discovered, and these are now so firmly established that the possibility of their ever being supplanted in new consequence of new discoveries is exceedingly remote. Thanks, everybody, and time to go home. That was what he said. He was a member of the Royal Society, and he announced that in 1894. So if we had all listened to what he had to say, we would have packed up our bags and none of us been STEM students. But we're here more than a century later, still discovering new things. And the interesting fact is that he himself was one of the people who laid the groundwork that brought quantum mechanics in, that brought us into the modern era of physics, which was largely born out of experimentation that happened right around this time. You may know him from the Michelson and Morley experiments. Speaking of which, one of the ongoing debates was whether the ether was real or not. What was the ether? Well, there was this idea that there was this medium that propagated waves and that we moved through the ether, and there was a kind of like an ether drift as the Earth went around the sun, and this might be what was propagating waves. So one of the experiments that he did was he was actually looking for the Doppler shift. You know how like when you have a fire engine going by and it has the siren going off and you hear the pitch of it changes depending on whether it's oncoming because the waves get compressed or if it is driving off away from you, in which case they are spread out and you hear the different pitch. So the idea was that if we are in fact drifting through the ether as we are spinning around the sun, that this would be something that we would be able to measure. And the idea was to go ahead and try to measure this using light. So this was actually set up using a series of mirrors and a light source up in some mountains, and then the idea was to measure how long the beam took to travel in those directions. So the idea was that if you made the distance large enough between where they were being measured, that you would actually be able to physically measure the distance of like you would be able to see that it took longer to go in one direction than the other. And so the idea was that you see how we have this system here. This is a mirror here. It's a beam splitter. So if you're familiar with spectroscopy, you know something about beam splitters. But the idea is you have the same beam. So you have a single light source here. And so what you're doing is you're sending the beam out to this mirror, and then it's going to come back. And then you would detect how long does it take to go out and come back, which is going to be pretty short time because light travels really fast. But what they did is by using this half silvered mirror was that it also sent a beam out to this mirror and it would also come back. And so somebody else would be sitting here watching, right? So somebody was manning this light source and somebody else was sitting over here. So this is Michelson and Morley were the two who did this. This particular setup is in a pool of mercury, which is not necessary. This is for allowing it to twist, but anyways, that's not how the very first one was done. But this setup is all relevant here. And so what they did is they measured how long the light took to go in this direction and then also in this direction, right? So you can, if the distances are equal, then the light should arrive at exactly the same instant. And so the idea is you make the distances large enough so that the error in the measurement would be small enough that you could actually take a measurement. And that's what they did. And so the idea was that if you had this set up so that one direction was going to be in the direction of the Earth spinning, that if there were such thing as the Doppler effect, you would be able to measure it, just like you can detect the change in the pitch of the sound waves. And what they found is that there was no evidence for that whatsoever. And so what we saw is that the speed of light does not depend on this traveling distance or anything about this mysterious ether. So the conclusions from the Michelson and Morley experiments was, well, first of all, it was asking the question, does light travel at different rate relative to the Earth's rotation in the luminous ether? And if the light behaves as a classical wave like sound, then it will, but if not, then we are moving into the unknown. All right, so light does not require the ether to propagate, so it is not like a classical wave. This was the first hint that light is somehow something different than other matter and stuff that we work with. The speed of light is a constant. This was very important for Einstein's theory of special relativity in 1905, and this established that the speed of light is a universal constant, the C that we love and know, and also the particle wave duality soon would be something that would come out of that. But let's not get ahead of ourselves. So then, up to that point, though, however, it is understandable why people might have thought that there was no other things to discover. I mean, there were quite a lot of things that we already knew how to do at that point. I'm thinking like 1890s. US was recovered from the Civil War. US had also been the start of the Industrial Revolution. It was also starting to take hold in some countries in Europe. We had quite a few things that we had already unraveled, and people were feeling like they pretty much knew a lot in chemistry. We had the concept of the molecule by Stanislaw Ganizano. We had Dmitry Mendeleev, periodic table. So the periodic table had already been organized, although nobody knew why it was organized the way that it was. But we had a substantial periodic table. We also had the calculi, the aromaticity of benzene. This was already known at this point. So those were some pretty amazing things. In physics, Isaac Newton, this was old hat by this time, Newtonian dynamics and the calculus. Don't forget, Newton not only thought up how to think about gravity, but also worked out his own version of calculus. This is why calculus and physics are so intertwined. Comte Joseph Lagrange and Sir Walter Hamilton had the Newtonian dynamics applied to planetary motion, elasticity, and hydrodynamics. So we now had those fields working. Count Runford and James Joule, this was the equivalent of heat and work. We will see much more of their work when we get to thermodynamics. C.D. Carnot, the formulation of the entropy and the second law of thermodynamics. Again, fundamentals of the thermodynamics portion of this course. We will definitely be back to some of these famous scientists' work, even now today. Electricity and magnetism also had substantial progress. So James Clerk Maxwell had unified optics with electricity and magnetism, which was a major breakthrough, and Heinrich Hertz demonstrated the wave-like properties of light. And this will become quite important for what we are going to be talking about. Hertz, the measurement Hz, you may be familiar with it. It means second to the -1. It's named in honor of Heinrich Hertz. And it is because it is how many cycles of the wave per second. But despite all of those amazing discoveries that we had, even at the turn of not 2000, but in 1900, which, by the way, may feel like a really long time ago, but I mean, I know people who were alive then. They seem very old to me, but it somehow feels like something you could reach out and touch. I mean, it wasn't that long ago, and that just reminds us how new the field of quantum mechanics really is. And in fact, several people at Wesleyan had some role in the development of that field. Um, Despite all of these amazing advances that we had, there were some hints that there might be more than just calculating out to the nth decimal place to do for work here. Something might be wrong with the world classical view because this was about to crash down. And a lot of this happened because we started having some observations. Part of it was from technological advances and just people starting to pay attention. And we started to think, there might be more out there than just the classical world, which we had done such good progress in explaining. So today, we're going to see a series of case studies and a few other tidbits of information. It is sort of like a puzzle. And by the end of today's lecture, I hope you will see how all of these pieces fit together to make a very elegant picture, a very strong argument that quantum mechanics is real. This is something that we really need to know in order to explain modern physics as we understand it and explain the world as we know it, consistent with what we are able to measure. And the very first one of these was black body radiation. So what exactly is black body radiation? Well, as it turns out, actually, one of the places where you may see black body radiation is the incandescent light bulb. It is the filament glowing. When you heat up metals, they tend to give off light. Here is an example of some metal being forged with the hammer here. And if you've ever been to like any of Jamestown or any of these other places where they have these exhibits for like how people used to forge things, you can go and see metalworking being done right before your very eye. Here is an example of how this is done. And so the colors, contrary to popular belief, red is not the hottest. Red is actually pretty cool. Here is the heat colors and the scale, and these are pretty hot temperatures. I mean, 1200 degrees is this is Fahrenheit. That's pretty hot. That's hotter than your cooking oven, which usually goes up to somewhere around 400. This is pretty hot. You don't want to touch this. But in fact, the temperature scale goes from red, and then of course the hottest color is actually the blues and the whites. This is only just showing you the metal colors, but yeah, our idea of red hot is really actually not correct in the grand scheme of things. But this describes how this radiation is given off. It's that light you can see. And so the Rayleigh-Jeans equation describes what the intensity of the light that is given off. So we have IV dV equals 8 pi kBT. We'll learn more about exactly what all these things are. But for now, this is just a number. T is the temperature. V squared dV over the speed of light to the third power. I mean, it looks great. You go to physics books and they tell you, like, here's some equation. Okay, wonderful. I wrote it this way for a very particular reason. So this is our variable nu, and I wrote it in a calculus way because I wanted you to see something. This is the dependent variable. This stuff here is basically some constant. I mean, you'll plug in, okay, 8 pi, you can understand that. C is a constant. KB, you may or may not know what it is. It's some number. It's the Boltzmann constant. Temperature, you may argue, oh, well, that actually changes, right? But we're holding the temperature the same, right? Okay, and so what we see then is that effectively we have a function of V. Now, what kind of an equation is this? If you had to graph it, remember your calculus days. F of x equals some constant times x squared. This is the form that we have here. So it's a parabola. It's a parabola multiplied by some constant stuff, effectively, is the general idea here. Now, when we actually look at black bodies, now this happens to be about stars, which also have black body radiation, but doesn't really matter. The key thing is that this does not look like a parabola, and I just gave you an equation of a parabola. So what's going on? Well, that's precisely what others were wondering as well. And there's also another problem with this, and that is that x squared x squared less than 0 doesn't make physical sense, right? So we're only looking for the values above 0 in the right-hand side of the parabola, if you will. And so the problem is that, well, if it were really true, we would have solved the energy crisis because there would be no shortage of energy, and that's not true. All right, so the problem is black body radiation does not actually follow the classical prediction, right? It does not follow the x squared prediction. It has those other forms that is definitely not the parabola. And higher frequency energy increases without bound, which is not physical, right? So what that would say is you simply just make a higher frequency and you have as much energy as you could ever want. So there's no energy crisis. What is everybody worried about? Well, it's not true. That's the thing. So black body radiation understood using classical equations is not working because it doesn't match what actually happens, and it's not true that we can just make as much energy as we feel like. So Planck came along and he had a solution. So he was thinking about oscillation of electrons in antennas. So we knew about radio waves and electrons jiggle around in the antennas, and this is how you get a radio wave. And so he was thinking, okay, so suppose it's something like oscillation of electrons. The oscillations and therefore the energies would be quantized. So he wrote this equation here, energy equals N. This is the whole quantum thing, HV. So this is the frequency of the radiation. H is Planck's constant. N is integer, and E is energy. So Planck put this in here. So basically H is going to be a proportionality constant, and he worked out what number it would be and substituted that in. But the whole point here is that we now have this idea of the quantization of the N, right? So N can only be integers. And what that means is that the energy then would be quantized because you'd always be multiplying by some integer here. So you will, it's possible for it to be another number, but it would be multiples of that. So Planck's equation then revise the Rayleigh-Jeans version of the equation. And so here is a new equation that we can use. So rho of V and T. So this rho may seem a little bit strange because we had I there before, but rho actually means the same thing as I in the sense that it is the energy density per unit frequency, which if you really think about it is really what intensity of light is telling you about. It's telling you about the density of light at that point. That's what the intensity means. So if light is more intense, then it's very bright in a small area. And if it's not intense, then it's not. And so that's why we have also the density measurement showing up here. So this is Planck's version of this, and notice that Planck's equation corrects then what these values would need to be. All right, so I'm just going to take a few notes here. All right. All right, so the next case study is the photoelectric effect. Let's take a look at this picture. Can you recognize this as some device that you are familiar with? In the beginning, it may not look that familiar, but I bet actually you do know what it is. So have some light hitting a metal surface, and I see some electrons are coming off. It's here in a vacuum chamber. And there's a battery down here. Do you know what it is now? Ammeter is measuring. This is a solar battery. I actually have one right here on my watch. This is a solar watch, and there is a little ring around the outside here. And this is it's actually a little solar panel on the watch, and that's why I like this watch a lot. I use it when I do hiking and stuff because I always know I can recharge it without a source of electricity. I just hold it up to the sunlight and it charges, and this is how it works. So Einstein is the one who actually worked all of this out. But anyways, let us let us take this step by step. So Becquerel was studying the effect of light on photovoltaic cells. Can you make so when we don't mean live cells, we mean like metal cells. And so when the light comes in, that's this over here, incident UV radiation comes in and strikes a metal, which has electrons that are in a C, right? So in this situation in metals, actually the electrons are not tightly bound because they are, well, we'll see when we get into quantum mechanics why they are not tightly bound. But when you strike them with the incoming radiation, it is possible for them to come off, and this is how we generate electricity. In the classic view, the intensity is proportional to the square root of the amplitude of the field um, of the irradiation. Oops, and there is a typo there. This should say of, sorry, 16, it should say of. As you increase the intensity, you also increase the amplitude of the electron oscillations. So the idea is that in the classical view is that if you just put a brighter and brighter light, you should get more and more electricity coming off, right? I mean, that would kind of make sense because if they're oscillating more, then it should be easier to eject the electrons. And so this means that there should be a threshold intensity I to eject electrons. So in other words, you could say, all right, well, here's here's a photo cell, and if you want to start charging the battery, what you should do is you should just change the intensity of the light, right? So it's going to be bright enough, and then it's going to start making electrons. And just to be clear, there obviously this isn't going to charge if there's no light, so there is some truth to that. But the point is that actually there was there was a frequency threshold that turned out to have some important role in all of this. So the contradictions to the classical view that all that's happening is you just need to have really bright light to get electrons to come off is that it actually mattered what the frequency of the light was. In other words, the color, right? So how do we see color? Well, color is a different frequency, and we know about this from using prisms to break white light into the rainbow. And so equals HV, reds is for the photons come in, so you have a radiation. So if you have a certain below threshold frequency of light, the issue is that you have that it might not work, right? So red light is a shorter wavelength, and then the violet is a longer, right? So Becquerel was studying about this. So the ejection of the light from the photovoltaic lights caused the electrons to be ejected. And so the kinetic energy of electrons is independent of the intensity of the UV radiation. I mean, we do say this. I mean, this doesn't mean that if there's no intensity, it's not going to work. But it's like surprisingly not proportional to the intensity, right? So you can have a very high intensity of the wrong frequency, right? Like if you only shine red light at um, very high intensity, it's not gonna work, which was weird because you could just shine the light in a different color on there and it would have the electrons get ejected and you would get the photovoltaic effects. So it's not the threshold intensity I, but rather the threshold frequency. And I see there's another typo. Sorry. But rather the threshold frequency characteristic of the metal for the electrons to be ejected. So that was something that didn't entirely make sense. And so Einstein is the one who came along and figured all of this out. So the radiation itself is quantized, was his idea. So the radiation exists in the packets of energy, which we know as photons. So this is Planck's equation. So the idea was that, well, Planck had thought up this equation in a different situation. He had thought out this in the black body radiation. But Einstein said, I wonder if this also applies when we are dealing with the photoelectric effect. So now we have this equation getting applied in this situation. So from this follows that the energy of an ejected electron in the incident is going to be the incident energy minus the amount of energy to escape from the metal surface. So in other words, you have a work equation. So here we have 1/2 mv squared, which you may recognize from physics is the kinetic energy equation. So this says the kinetic energy of an ejected electron is going to be, well, how much? The energy incident of the UV and then the work it required. So there is some like energy to like jump out off the metal. And so this H V0 is going to be that amount of work. So this is known as the work function part, and this is the amount of energy for the incident UV light. And however much is left over will be the difference that you get, and that will be the kinetic energy of the ejected electron. And so this then represents Einstein's key insight into how this all works. And the interesting thing is that there's an N right here. Again, we have this idea of the application of an integer value, which was something that was not really known in classical physics. That brings us then to Planck's constant. So one interesting thing is that Einstein and Planck both arrived at the same constant h from very different roots. So Planck had done it for a different reason, and now Einstein saw it, right? So in the beginning, nobody really believed Planck, and then Einstein's theory of relativity also used it, and so people started paying attention a little bit more. And so the H is really a proportionality constant. It is something that tells us the proportionality between the energy and the V. So this added credibility to the idea of quantization. And so H is basically a proportionality constant, and it tells you how much energy corresponds to a given frequency. So high frequency is high energy, and H sets the scale for how much that actually is going to be. All right, next observation. This is line spectra. And in fact, this is something that you can observe yourself. You might have even done this experiment. It's a fairly common one to do in high schools. This is the line spectrum. So let's understand what this is. So when you look at natural light, you put a prism up, right? You should be able to split that into the complete rainbow, and you have all possible colors there. And that's because the light is coming out with all frequencies. But if something were not a full spectrum, then you would not see it. This is exactly what we talk about when we talk about light bulbs. I know about this because I do tend to get headaches from non-full spectrum lighting, like fluorescent bulbs. What exactly does it mean? Well, it means that the light may be emitted in not the complete spectrum. So atoms, when they're subjected to increased temperature electricity, will emit electromagnetic radiation with a characteristic discrete frequency. This emission spectrum makes a line pattern. So this is what the full spectrum looks like. Here's the hydrogen emission spectrum, which we notice is missing quite a few of the values, right? So there's these bands. And that's what's being shown up here, right? That's missing. And so why is there these specific ones? That was something that you can actually observe using a handheld spectroscope, and this will show you what the lines are. Discrete emission led to very specific wavelengths of light being there. So why did they have the stripes? Well, the effect is because the light being given off is only being given off in certain frequencies, not all of the frequencies to give you the whole rainbow. And that's what we mean by the line spectra, right? You get these lines in the spectrum. It's not the whole thing. And so, well, how come? Well, nobody knew at that time. Maybe you know already. So, as we were mentioning, light bulbs are actually from the black body radiation. They have a filament in them, and so light from an incandescent light bulb happens when you have the glowing. Fluorescent lights give off light, but they are not full spectrum. They are typically having some inert gas in them, and also it is the mercury that is in them, some very small amount of mercury that is doing the glowing, and it is usually that which is giving us the color or the lighting in the fluorescent light. But you may notice that fluorescent lights do not behave the same as incandescent light bulbs. That's because fluorescent light bulbs are not full spectrum. Why are they incomplete? So scientists believed that the emission spectra were reflecting information on the underlying atomic structure, but they had no idea why. So empirical observations of a scientist called Balmer. So the frequency of the lines of the hydrogen spectrum fit in equations. We just saw the spectrum for H and it's not full. And he empirically noticed this pattern. Okay, so the V squiggle is the wave number. This is 1 over lambda because it's just more convenient for measuring. So spectroscopists tend to do this. He could plug in this number here, and he had 1 over 2 squared minus 1 over n squared centimeters to the minus 1. And this is what he got for the wave numbers. And then he noticed that you could plug in these numbers 3, 4, 5, and so on. Where n is an integer index labeling the observed lines. And this was the an empirical constant, which I've labeled here as the Rydberg constant, but actually Balmer saw it first. And Balmer didn't know why he had this number. So Rydberg had a look, and he derived a more general form of the Balmer equation. So here, in this case, notice the things that have changed. We put an R here instead of that number. We have, and the equation still has generally the same form, but notice that Balmer's had 2 squared, and this one is n squared. Right, so we're going to have NF and NI. This is for initial and final. Basically, you just need to have 2 different ends, with the ends are going to be, again, it will eventually turn into the principal quantum number, but for right now, what they knew is that they were integers, which is why they are n. So you have 2 integers, and Ni is the larger of the 2. So this is a transition. You may know where this is going to if you know something about this. You may have seen this in Gen Chem. So all the line spectra hydrogen can be accounted for if you consider the difference of the 1 over n squareds, for which Balmer had 1 constant. All right, I see we have another typo. Sorry about that. The n denotes energy states, and we have this quantization again, but nobody really knew exactly why we needed to have that quantization. So let's just take a look at this. So as things progressed, people then started saying, well, let's try out a couple of different combinations of this. So people started realizing that the Palmer series was just a special instance of this more general trend. So the Lyman series has NF being 1, so this is the ground state, and then you have NI as 2, 3, 4. So in other words, the NI can be anything higher than whatever NF is. So you see if it's 2, then you're going to start at 3, 3 you start at 4, and so on. And so we had these different scientists studying the light in these different regions. Now, fun fact, why do you suppose that the Balmer series, which actually doesn't use the ground state of n equals 1, wasn't the first one? I mean, you'd think that would be the easiest one to discover. Do you see why? The reason is because the Lyman series happens in UV light, and you can't see it with the naked eye. Balmer is the lowest series you can see in visible light, and that's how he noticed it, because he saw it with visible light. Now we need to do a little interlude. So this is not a particular case study where something unusual had been noticed and then people worked it out with a solution that relates to quantum mechanics. So de Broglie was doing something a little bit different. Louis de Broglie made some very important contributions. He postulated that matter has wave-like properties. Wave-like and particle-like examples existed, so wave-like dispersion of white light into a prism, but into the spectrum was known. Photon-like particulate was the photoelectric effect, showing that radiation has fixed packets of energy. So this is where the particle-wave duality is starting to come into play. So the particle-wave duality of light seems to be happening. So at this point, it was pretty well established that light was not a normal wave like sound is a normal wave. This is not like a wave rippling on the surface of a pond. So de Broglie's idea is that if light can be particle-like, then maybe matter could be wave-like. What would happen if that were true? Well, that's part of what he was trying to understand. So one thing that would be useful for us to understand is how to actually measure the wavelength of light. So this actually can be done with a pretty reasonable experiment. So what you do is you have some laser light source. So here's your laser, and you have a grating element. Now what this is sort of kind of like a prism. It breaks the light up, right? And so what happens is you have the grating that will break up the light and send it into the different locations. And so what we have here is when you have the grating, that you have, all right, some distance from the grating, and then here's a screen. So in the case of this, the screen could be, for example, a piece of paper. So here's somebody getting these beams, and they are shining onto the paper, and what they could do is just mark the place of the beams. And because the diffraction will have multiple spots, I'm only just showing the main beam and then the first order diffraction. So that's what's here, but there would obviously be some others. Now, this picture was not exactly to the same scale as this, so beams do not bend like that. But anyways, hopefully you get the general idea. But the idea here is then that we have a triangle being created. So you have this theta angle. So if we were to look at, say, like this triangle right here, this is a right triangle. Here's your spot up here, and then you have another spot down here. And so you see that what you've made is a right triangle, and so right triangle trig applies because you also know the distance between the screen, which is your paper, and the grating element. So you get some distance d right here. And now we're in the territory of triangle trig to solve what is going on here. So what you can do is you can use this information to figure out what the wavelength is, right? So this distance right here is gonna be telling you about the wavelength. So you can use d sine theta equals m lambda, where lambda is the wavelength, d is the spacing between the adjacent slits on your diffraction grating. So you need to know how your diffraction grating was made. Your theta that we saw in the triangle, which is right here. And then m is your diffraction order. So you need to know how many spots away you're doing. So if we do one spot away, for example, m will be 1. So that's where you would measure. And you can use this to figure out what the wavelength is going to be. So matter obeys the Planck-Einstein relation as well. And so this was a very interesting idea that de Broglie had. So here's the particle wave duality. So if light can be a particle-like, and so too maybe matter could be a wave-like, that is the idea. So we have E equals hv and V equals c over lambda. This is for matter, and this one is for wave. So if duality holds, then we can combine these two equations, right? So you have V right here, and here's what V equals, and you'll take this thing and you'll plug it in there. And that's what we did here. And then we could solve for lambda by rearranging this equation. So we just apply the algebra, and voila, we have a new equation. And the question is, well, what does that equation mean? So Einstein also showed for photons E equals PC, where P is going to be your momentum times the velocity, right? So this is known from physics equals P equals mv. You probably heard about that in your kinematic studies. And so then if we take this lambda equation from above and we have the energy here, and energy is PC, we can do a bit of plugging and canceling to get lambda equals h over p. This is the de Broglie wavelength. Now, wavelengths are not supposed to be for matter, right? I mean, we don't normally think of like, I don't know, wavelength of a pen. I mean, what does that even mean? But that's what the theory says. And so it also says, well, the wavelength may also pertain to very small particles. And this is where de Broglie was going with all of this. So what this means then is that the de Broglie wavelength could be calculated for subatomic particles as well as for larger everyday objects. And that's what I mean. This here drive has a wavelength. My pen has a wavelength. That's weird. But this is quantum mechanics has some very weird applications. Modern physics is very strange and non-intuitive in a lot of ways. So this says the de Broglie wavelength can be calculated for subatomic particles as well as everyday objects. The lambda is large for small particles, and thus an important thing to take into account. And that's why we're going to be looking at the wavelength in quantum mechanics. But the lambda is very small for macroscopic objects and thus is negligible for our understanding of everyday things. So one might wonder, well, how is it that for centuries, literally, we were going along calculating things just fine? I mean, what about Newtonian dynamics? Is it all wrong? Did we somehow make a mistake here? But the way that we can resolve all of this is that the wavelength is so tiny or an object that are on the scale of everyday things that it doesn't actually play in. But the wavelength is going to be very large for very tiny particles. And so the wavelength property is going to be very important for us in understanding subatomic particles. And in fact, that is going to have a lot to do with how we understand where electrons go, which will be important for doing things like figuring out how bonds work, because wavelength is key. So we need to think about wavelength in the very tiny quantum mechanic world, but in kinematics, you can skip it because it makes the calculations a lot harder and it does not change the outcome in any way that would be perceptible or measurable in our everyday lives. And that is why it is not inconsistent. All right, next thing we need to consider, the next piece of the puzzle. So, plum pudding model versus the nuclear model. Which one is correct? I'm sure you all know that plum pudding is wrong, but the nuclear model is right. How do you know that, though? I mean, if you, I don't know, landed on an island and wanted to inform the people of what had happened in physics, how would you explain to them how we know that the nuclear model is correct? Well, as it turns out, Rutherford was thinking about that exact same thing, and he worked on an experiment to understand this. So the idea is the electrons are in the cloud, right, or on the outside, and the protons are in the nucleus. But we didn't actually know that at the time. And so, I mean, you can't just, make a magnifying glass and take a look. So how did we do it? Well, what Rutherford did was he worked out how to use a radioactive substance to send off an alpha 2+ beam. Now, the protons in the atom are going to also have a positive charge, and like charges will repel. That's the whole premise behind all of this. So what you do is you have this gold foil, which can give off some particles, right? So you put a very thin gold foil so that the beam can penetrate. So it's thin enough that some will get through. And what you want to do is then put up a detector screen. So this is like a film. I mean, these days we don't use this kind of a detector, but it's like a photo paper here. And so if a particle goes and hits it, you'll see a spot on the paper. So what I've done here is I've taken this view here, which is like an overview of the experiment, and here is a view of what's happening. Obviously, these are schematics. So here is our the deflection screen for the detection, and here's something happening, and the beams are coming up. So in the event that it was the plum pudding. Let's actually just go back and take a look. So you see that the pluses and minuses are more or less canceled out. So if the beam were going through and it was pluses and minuses being next to each other, the beam wouldn't really have a problem because the field would be very small, right? Because, or maybe not even detectable because the beam wouldn't be affected by the charge because it's neutralized. But in the case of the nucleus, which is what's being shown here, if you have these incoming particles that feel the same as the nucleus, they're going to repel. And so there will be a very large field here. So the electrons are far away and cannot counterbalance the field that is being generated by this giant nucleus that's got lots of plus charges all stuck together. And so when the beam comes in, if the case were that they were both positively charged, it would come along and some of them are going to deflect off, right? So some of them are going to hit and just go back, but some of them are going to be on the side of it and they're going to deflect off to the side, which is what's happening here. And so when we take a look then at the film, the idea is that they're deflected in all these strange angles. And that's exactly what happened, which mitigates the possibility of the plum pudding model, that's J.J. Thomson's model, being correct. And it was the nuclear model posed by Rutherford that was actually correct. And that was how we know. So this is just a little summary of that. So the diffraction pattern distinguishes between the two models. If deflectionless spots do appear, it's a repulsive field. But if they only appeared straight ahead, it meant that there wasn't a field being felt because everything was neutralized because they were all intertwined with each other in the plum pudding model, and which didn't happen. And so the result supported the dense nucleus atom model of the atom, which is the one that we know. So the nucleus is much more massive than the electron. It moves more slowly than the electrons because it's more massive, and the electrons revolve around the nucleus. The Coulombic attraction between the positive nucleus and the negative electrons holds the electrons in orbit. Well, anyways, there will be some things to say about exactly that. But this is where we were at this point. So that last statement that I said leads us to our case study number 4. And that is the catastrophe of the collapse of the atom. So let me explain what I mean. This is the Bohr model of the atom, supported by the Rutherford experiments. So here the electrons are buzzing around the outside, and we have a nucleus with the protons and the neutrons in it, and the electrons are going in orbit. Great. I mean, everything's wonderful and happy, right? There is a problem, however. Spot the bug. So here we have a cute little lightning bug up here. Bug in code means there's something wrong here. So let's take a look at this and see where the problem is. So you have two classical forces. Here's a Coulombic force. This is for charges, right? Goes over r squared, right? And that's fine. So the distance is closer, the attraction or repulsion is stronger. That's all true. Some permittivity, constants, shielding, and so on. This all seems pretty reasonable. And here's the centrifugal force. You may recognize this, actually both of these from physics. mv squared over r. I mean, these are the correct equations, right? We have two forces. And so we just said that the electrons are spinning around the nucleus, so there should be a centrifugal force, and then there should be a Coulombic force, right? So these two things are, one is pushing out and one is pulling in. Right, so Coulomb is pulling in and centrifugal is pushing out. And so how do you solve this thing? Well, you have two forces and you equate them. And this is a force balance equation, and you figure out, okay, there'll be some radius, and that is the location of where the electrons are going to spin around, right? Well, what's wrong with this? I mean, sounds correct, right? The problem is when you compute the attraction of the electron to the protons, it's balanced by the force. As the electrons orbit the nucleus, they will emit an electromagnetic radiation. So energy is being emitted. So that means that the force is going to get smaller and smaller. So the energy would decrease. Well, if the energy decreases, what's going to happen? The balance will be off and the electron will move a little closer to the nucleus. If the energy decreases, then the electron will eventually crash into the nucleus as it runs out of energy. So you'll see what will happen is it will go in a little closer and closer. But electrons are not supposed to be in the center. They're supposed to be orbiting around. So how come atoms don't collapse? You see that this poses a little bit of a problem because atoms aren't collapsing all the time. So the classical prediction says atoms will be unstable and that they like implode and I don't know, something very bad will happen. But atoms have been around and they've been around for a really long time. So what's wrong here? Well, this is where Bohr came up with a solution. So this is Niels Bohr. So he said, well, all this other stuff has been solved by quantization. Maybe we should just put a quantum number in this one too. Um, so, but let's talk about it in a little bit more serious way than just that. So when you have waves, when the waves are out of phase, they have the constructive and the destructive interference, right? So when you have two waves, what you do is to get the wave you actually have is you sum the two together. You probably know this from your physics class. But if you only had waves that were allowed to be in phase with each other, then you wouldn't have the constructive and destructive interference. You wouldn't have any interference at all. So what it may be is that somehow the allowed orbits only allows the interference to be that you don't have interference so that the wave is stable. And the way that you get this is that whatever the wavelength is, that wavelength again we were mentioning before, would have to be in phase. And so if you had the circle around, the wavelengths would get out of phase. It's like the spirograph. If you have it in phase, the spirograph only just keeps repeating the identical pattern, which is not very exciting. But in quantum mechanics, that's exactly what you want. Whereas when they're out of phase a little bit each time, like this pattern here, right? So you see you go around and it doesn't exactly quite line up. That's where the problem comes from. So the electrons go to the distance from the nucleus such that their wave fits around exactly so that you don't have the so you only have constructive. So because this one would have the destructive interference, which would make the problem happen. So Bohr is the one who suggested that this is the situation. Whatever the wavelength is, then that's going to fit around and that will determine your distance from the nucleus for this radius right here. Oops, and we have a fire drill. Hold on. Gonna escape. Oh, it just stopped. Haha. Maybe we're on. Right, guys, we gotta evacuate. Nope, it's real. Sorry, guys.